So I'm Steve Eikenberry. I'm a professor here at UCF in CREOL, also the joint appointment in the physics department, planetary sciences track. And my talk is going to be about PolyOculus, astrophotonics in action. So my background and my group's background is in optical and infrared astrophysics. I'm a Ph.D. astrophysicist by training. And previous to coming to UCF last year, I was a professor in astronomy and in physics at the University of Florida for about 20 years. And I was a professor at Cornell University prior to that, again in astronomy. And however, our group works on a bunch of science areas, black holes, neutron stars, dark energy, and so on, where the tools to measure the things that we want to study did not exist. So I ended up spending a lot of my time, as you can see here, working in applied optics. And that led me to move to CREOL last year as a professor of applied optics, and particularly pivoting into an area into space photonics in general and astrophotonics in particular. And by that we mean applying photonic technologies to solving problems for astrophysical studies. PolyOculus is one of our flagship technologies in that area. It relies on a recent evolution in some key commercial off-the-shelf technologies, particularly low-cost, sort of what used to be advanced amateur telescopes, like the one shown here from Meade Corporation. There are other vendors like Celestron, Ioptron, and so on. And it turns out that they've evolved to the point where with some active control with a guiding system, you can actually point them and steer them about as well as you can any of the large professional facilities. But they're much, much cheaper. And then meanwhile, to achieve that, we can outfit them with low-cost, very small package single-board computers, like a Jetson from NVIDIA. It's about a $200 board. And we also have very low-cost $200 or $300 CCD or CMOS sensors to enable the acquisition and guiding. So we then couple that with some key advances in optical fibers and photonic technology to take a large number of these telescopes and link them all together to create a distributed aperture, larger area telescope. And we can do so with a cost per square meter. And that's the key metric for an astronomical telescope is how many square meters do you have? And our cost drops by over an order of magnitude when we do that. And that was our motivation for PolyOculus. Application areas, I'll talk a little bit about the astrophysics parts of it. But also they have applications in atmospheric LIDAR and also in space-to-ground optical communications that we're working on right now. So just to kind of zoom in a little bit, you can see our telescope here with a small acquisition and guide box at the bottom and then a cable feeding out. So the acquisition and guide box, you can see here, these are all 3D printed parts. Much lower end additive manufacturing, but still doing additive manufacturing for both cost and particularly weight to keep the mass down on these things. A cross-sectional view of that thing, the light comes from the telescope. Most of it gets reflected by a mirror over to an acquisition and guide camera through a lens here. So we can actually look at the sky, track and guide, keeping the stars in the same place. But in the middle of this mirror, it's actually a lithographically etched spot on a transparent substrate that lets light pass through from one target and it's relayed into an optical fiber. We can then take, say, 7 of these things, 7 telescopes, point them at the same target in parallel, take those optical fiber outputs and combine them through a photonic lantern. And basically that's what's shown here. It's a kind of technology. It's an adiabatic taper that was invented in the mid-2000s by one of our collaborators, Sergio Leon Saval. And basically what we do is we can feed individual optical fibers into low index capillary tubes and then taper them to follow a specific profile in terms of the diameter and index of refraction of the glass in those fibers as a function of length along it, so that over the length of about a ballpoint pen like this, we can couple all 7 of those fibers into a single multi-mode output. And so this has a lot of applications for us as light couplers, Also, I won't talk about them today, but wavefront sensors, light splitters, and biomedical microscopy are other areas we're using photonic lanterns. A key challenge was getting the efficiency up. Photonic lanterns have been around for a while, but at efficiencies of 50 or 60%, they aren't really usable for this application. As you can see here, this is a paper by my graduate student, Christina Moritis, that says submitted, but it was actually published in Applied Optics a little over a year ago in 2021. And we're achieving in the 90s percentage efficiency. So they're quite low loss. This is invisible light that she's showing here. Once we get up to longer wavelengths, approaching a micron, our efficiencies actually get up to about 97, 98%. So they're really excellent efficiency couplers. So again, we can then take our 7 telescope units here, combine each one in the photonic lantern, and then we can combine that with a switch that will either let us send that light out to a scientific instrument, a spectrograph or some other device. We also have a power meter that lets us check and see that we have these things all aligned. Or we can send it to the next level. What do I mean by next level? Well, if we have 7 telescopes linked to a single fiber now at the output of the photonic lantern, we could take 7 of those arrays and take those 7 fibers and connect those into an even bigger output. And now we can easily synthesize, say, a 2.5 meter telescope. And again, this all relies on the low cost, but also fully automated approach. I should have mentioned that earlier. We have to fully automate these individual telescopes so that they will slew to a target, acquire it, send the light down the slit, keep it there, and they even automatically keep their focus tracking as well, so that we can combine the light in a timely and usable manner. So we're doing that now though with the PolyOculus. And again, just to show the cost, a standard 1 meter telescope is about $1 million these days. We can build an equivalent PolyOculus for about $150,000. With a 2.5 meter, which is a 7x7 array, so 49 telescopes, it's a $1.6 million cost that we can now do for about $120,000 per square meter. So, sorry, these are costs per square meter, not the net costs. So the 2.5 meter is about $10 million. And we can do that for under 1 million. And then this keeps going all the way up to the extremely large telescopes. The cost per square meter of those is 1.4 million. Of course, you've got 900 square meters, so they're over $1 billion telescope. And we can actually build an equivalent system for the low price of about $70 or $80 million. It's still expensive, but actually not all that terrible considering what we're spending on telescopes these days. One of our key application areas for this is the spooky thing in the universe called dark energy. So you all may know that our universe is expanding. Edwin Hubble discovered that about 100 years ago, that there was a big bang and the universe has been expanding ever since. However, what we found when asking the question a few years back, how much is that expansion slowing down due to the impacts of gravity? It's a way of weighing the entire universe. And a couple of my classmates in graduate school found that the answer was negative number. That the universal expansion is actually accelerating. It's getting faster with time. They won the Nobel Prize for that work in discovering dark energy. However, the way they did that was by looking at the shape of the universe effectively, rather than seeing anything accelerate over time. So we're trying to do what's known as the Redshift drift experiment, which is basically taking a large array. You can sort of envision a football field full of these small telescopes, all pointing at a high redshift quasar, all with photonic lantern linkages. We then combine that with the exquisite precision available from quantum sensing technologies like laser frequency combs coupled to atomic clocks. And then we actively stabilize a spectrograph to then measure the velocity of a number of features along the line of sight to the quasar. So these are galaxies in between absorbing some light. And those things will actually shift their velocity. So each one of these lines gives us the velocity try to show it here. The velocity to one of those clouds, those will shift by a small amount over time. It's on the order of, you can see here, on the order of about a centimeter per second per year of acceleration. So centimeter per second, that is a not particularly motivated ant crawling across your desk. So we're trying to measure velocities to that precision from the most distant objects in the universe, and then watch it, and then actually measure the changes in that over about 10 years. But we believe with a system that's about the same cost that the Department of Energy is spending right now on individual dark energy experiments, if we put one element of those, have it be this redshift drift experiment at that cost level, in about 3 years, we can actually measure directly the acceleration of the universe as delta V over delta T, which would then be solid proof that dark energy really does exist. So we think that would be a fun application. There are others as well in planet, extrasolar planet studies and so on. In addition, we can do atmospheric LIDAR. So again, low cost collectors like this can take the light, combine them through a photonic lantern into a fiber that we feed into our existing LIDAR systems. So we're building one of those to deploy at Arecibo Observatory next year. And then similar kind of thing actually for satellite communications. We can make very low cost ground stations for laser communications in the optical from space down to ground. And so I'll just wrap up there and say PolyOculus is a very low cost, flexible, dynamically configurable, and autonomously operating large area telescope system. Our cost per square meter is about 10 times less than standard telescopes. And we have applications from astrophysics all the way to telecommunication. And I'll stop there.